The Story of a Wave by Jamie Goodman. That's me! This short film will follow the story of a wave from birth to death. To do this, I'll be using diagrams and drawings to cover my main 3 objectives. These are: what creates wind, how wind generates waves, and what happens to these waves after they are created. Right, let's take it back. Take it back to around 149.6 million kilometres, the distance from the Earth to the Sun. Even with all this space between the Earth and the Sun, still a significant 51% of the Sun's radiation is absorbed into the Earth's surfaces. Although, due to the Earth's axis and spin, this creates inconsistent heating throughout the globe, but more on that later. Wind is created by pressure systems known as the atmospheric pressure. This is a measurement of weight pressing down on the Earth's surface. Air at the surface will rush from the high pressure to a low pressure. This action is more commonly known as wind. This is a result from the rising and the falling of the air in the atmosphere. The warmer air is warmed up by the sun and becomes less dense, therefore rising. This produces a low pressure on the Earth's atmosphere. As the air begins to cool down, it drops back down to the surface again as it is more dense. This creates a high pressure on the Earth's surface. This happens on both a local and global scale. This is more commonly known as a sea breeze locally. As the sun shines down, it heats up both the land and the sea, with the land heating up quicker than the sea. Colder air over the sea doesn't rise, but instead it rushes to fill the gap which was created from the warm air which has risen from the land. Similar to local wind scale, the sun heats up the Earth unequally. Due to the Earth's slant in its axis, this means the equator heats up first, then followed by the poles. As the sun heats up the surface in the equatorial region, air rises and travels towards the poles. This creates a low pressure. Air continues to travel to the poles, cooling more and more, until it falls back down to the Earth's surface, creating a high pressure. This air is then passed around the cells more commonly known as circulation cells. These are Hadley, Ferrel and Polar. Here is another angle of global wind scale. As you can see, the warm air rises between the Hadley cells and gets pushed towards the Ferrel cells in both the northern and southern hemisphere. As the air reaches the polar cells, it's the coldest it can be and therefore sinks back down to the Earth's surface. This then travels back to the equatorial region where it reheats up again. How are waves created? Wind miles out at sea forms a storm, which creates chop on the water as it drags across the surface due to friction. Ripples are formed and begin to move in the same direction as the wind is blowing. These are also known as capillary waves. These waves can grow bigger and bigger due to 3 factors: wind speed, wind duration, and fetch. Wind speed. The greater the wind speed, the bigger the wave. Duration. The longer the wind blows, the bigger the wave, and the last but not least, fetch. Fetch is the amount of surface area of the wave that is affected by the wind. The bigger the fetch, the bigger the wave. With that being said, capillary waves begin to merge as the top layer falls over the bottom, creating eddies. Eddies are circular currents in both air and water which press down on a surface. As the wind keeps blowing, the waves become easy to get hold of, making them increase in size. Before we move on, I'm just going to go through a few pieces of a wave. The wavelength is measured between the 2 crests of a wave, or between 2 troughs. Underneath the crest, circular oscillations are made, and it is these that move the water. These waves are called gravity waves, as they are now fully formed by the wind. Each has its own speed and period, which is the time taken between one crest to the other. Now then, back to these crazy circular oscillations. When the wave reaches the shoreline less than half the wavelength, the circular motion begins to squash and slow down due to the friction on the floor. However, the top layer of the wave carries on at the same speed, as it hasn't been affected by friction. This then makes the top of the wave to spill, creating a breaking wave at the shoreline. Here you can see a full wave equation, and this is what all the letters stand for. This equation helps us to calculate wave speed. On to our third and final objective. Swell is now freely moving in the ocean. As it gets closer to the shoreline, it can experience one of three processes which alter the wave direction. These are refraction, reflection, and diffraction. Refraction is the bending of the wave, and it occurs when changes happen from deep water to shallow water. Water travels faster in deep water. When it reaches shallow water, it is slowed down by friction. Here, the headland is what we're going to use as an example. The wave bends around the headland and makes it into the bay. Reflection. This is when the wave hits a straight surface and bounces it off. On a curved surface, if the object is concaved, the ends of the wave will hit the surface first. They then reflect back in and meet at the same point. This is called convergence. The middle of the wave hits the curved point at a later period. With a convex surface, the opposite takes place. Waves are reflected outwards, away from one another. Last but not least, diffraction. This is the change in the wave direction as they pass through an opening or around an object which is in front of them. As the wave approaches the gap, part of it will get through. The rest will be reflected away. The part that gets through will begin to arc due to the ends touching the sides of an opening. This creates drag and slows down the wave. This now concludes the story of a wave. Thank you for listening.